Okay, thank you for the kind introduction. Good morning, everyone. So apparently, I'm not an expert data scientist, so I'm an engineer, an industrial engineer, and maybe let's call it an apprentice citizen data scientist, as I have the privilege to work in the collaborative research center. And today I will give you the domain perspective on industrial data science from an engineering perspective. So we've learned from Ralf Klinkenberg that data science is a game changer, and the impact data science has on industrial production is significant. And we just listened all to the impressive and exciting talk from Katharina Morik, and I believe the potential industrial data science has became very transparent in this presentation. So what's actually the role of industrial engineering in the production in a factory? And this is easily explained looking at my research interests, which is time and motion studies, work system design, human-robot collaboration. So it's all about designing and running work systems. It's factory physics, how to run a factory, lean production. It's applying digital tools. And last but not least, one important research area of the institute became industrial data science. And was already mentioned when I did my PhD in Aachen. I did my first steps in regard to data science, actually applying unsupervised learning, self-organizing maps to the part family formation problem, which is basically automatic, which is actually clustering of part families. And coming back from Bosch to university, to Dortmund, I started further exploring the field of data science in production. And I was very privileged to have an environment here in Dortmund with the colleagues from computer science, with Katharina Morik, with the statistics faculty, Klaus Weiss, and last but not least, the guys from Rapid Miner, who were really very helpful in order to build up some expertise at the institute. And when the Industry 4.0, the Internet of Things, the Internet of Production hype kicked in 3 years ago, our institute has been well prepared for that. So I'm pretty sure you're all aware of this Industry 4.0, as I call it, the fourth industrial revolution, which is pretty much, excuse me, pretty much based on cyber physical systems and data science. And for us, the key question was, how does that change industrial production, and how does that change the role and the tasks of industrial engineers? And that's what I would like to talk about today. And that might be interesting for many of you guys who are in a similar position than we've been, let's say, 2 years ago. So we've seen this slide before today, and looking what is the state of the art in industry today, and I'm talking about not bad but good practice here, we find many applications which are focusing on descriptive analytics and diagnostic analytics. So what I've seen at Siemens and Bosch plants, many applications is the business intelligence and reporting in regard to manufacturing processes, which is basically observing what happened as a very important component of the daily continuous improvement and shop floor management routines. And additionally, we find a lot of applications in the field of diagnostic analytics, explaining what has actually happened. And I believe many of you have Six Sigma green belts or black belts in your companies who do exactly this, which is already data analytics. So from my perspective, good practice, state of the art, is descriptive and diagnostic. And we've already learned from Katharina Morik how huge the potential of predictive and prescriptive analytics is in this field. And I would like to share some use cases we did with industry partners in the last years with you today. So let's start with the area of time and motion studies, which is basically, I would say, the roots of industrial engineering, which go all back to Taylor and Gilbreth in regard to time measurement and standard times. And every one of you who is familiar with these up until today state-of-the-art methods is well aware that we are talking about applied statistics here. So when you do wafer time studies and you want to determine the accuracy of your measurements, you do hypothesis testing, so it's descriptive statistics. And we even have multivariate statistics, predictive models, which is regression analysis, which is applied in order to derive standard times, like in the MTM system, for example. So it's at least applying statistical methods have a very long tradition in industrial engineering. That's why sometimes we are called bean counters. Yeah? So, and the key question would be, what would be the benefit of advanced data analytics methods? And I believe Ralf Klinkenberg, he's already touched on this application, which is from the new product introduction process, and the use case is to predict the assembly time for new products in an early phase of product development, because when you launch a new car, all the managers, they want to know pretty early what the hours per vehicle or the hours per engine might be. It's one of the key KPIs in the automotive industry, and you have some ideas about the product, excuse me, but you do not know the work system yet. So that's the use case, and we approach this use case by applying data analytics, and we will learn more about this case in the presentations from Miele and Daimler today. It's just that I would like to mention that a major task in this project was to get the data right, as Katharina pointed out very clearly. So it was the pre-processing of the data, which took a lot of effort, and then, of course, training prediction models. What I forgot to mention is that, as in most use case projects, we are following the crisp DM process, which you can see here again, and we've learned about this today, and that gives a very good structure on data science projects. And I would say in many projects this has become a kind of standard procedure we follow to give a structure to the project. Looking at the evaluation, we've learned about anomaly detection, outlier detection. So we've applied unsupervised learning, clustering, which supports visualizing the data when it comes to supervised learning methods, models. Katharina has mentioned core and support vector machines, which give a very good accuracy. What we actually like to do is, in industry projects for evaluation of the first feasibility studies, we like to use decision trees, which are quite handy to visualize results in regard to the interpretation of results together with the domain experts. Yeah? And that's why I picked this example here. And last but not least, I mean, once you got the model working, you have to deploy it. And what we actually did is we have integrated the prediction models into state-of-the-art IT tools in the domain of industrial engineering. For example, Tycon for representing standard times, or a well-known PLM system, which is Teamcenter from Siemens. So we have achieved a pretty good level of integration, and you will learn more about this in the later talks today. So this is time and motion studies, and very closely linked to time and motion studies is workplace ergonomics. I'm not sure who of you is familiar with workplace ergonomics. State of the art is really conducting motion studies in the factory, in the field, which is observing work operations, the operators, and basically doing a manual ergonomic assessment, which basically means coding or classifying the movements you are observing. And this is really a big effort. This is really bean counting, as you have to do it manually. And as industrial engineers, we are working on how to make this task more efficient or automate this task. And this is actually state of the art. We came up with human kinematics simulation, human modeling, which basically is based on a kinematic model of the human operator. And what we actually do is we have, out of the kinematics information, we are running an ergonomics assessment automatically. But I mean, this is based on a computer model. What we are investigating in a moment is how motion capturing, which you might know from home, from computer gaming, Microsoft Kinect. This is actually optical motion capturing or inertial motion capturing, which is applying yaw rate and acceleration sensors on your body limbs for motion capturing. This system here we are using in our laboratory that comes from the gaming industry, and I believe this movie Avatar has been created using this motion capturing system. And this is something we've been discussing in our collaborative research center, how this data input could be used for automatic classification, which is automating this manual task of classifying. And Katharina came up with the idea that that might be an application for multi-layer neural networks, which is labeled, is running under the label deep learning. Deep learning is mentioned quite frequently nowadays, but that might be really an interesting application for this. And as a next step, is this something we have in mind, is basically having a copy and paste procedure from man to machine that the robot is copying the operator's task. So this is a bit of what our vision is, where we would like to use data science in the field of workplace ergonomics. So moving on, this is a very large field of industrial data science, which is production system design. So in production system design, the key principle is ideally you have one-piece flow in a synchronized, balanced production system. And state of the art is applying value stream mapping, which is basically analyzing the system in regard to material and information flow. There is line balancing, which you apply designing this synchronized system. And what is a key principle or key issue in designing and running a production system is all about the bottleneck. To control the bottleneck process within a value stream is essential. And many concepts for bottleneck control. There are actually some issues in regard to this bottleneck orientation. And the first issue is that these bottlenecks are dynamic. Yeah, it's like in this traffic forecasting. It's not always the same process which is the bottleneck. And the good news is, some years ago, we came with colleagues from Bosch, we came to an approach in order to identify the dynamic bottleneck within a value stream, which is basically very simple applied factory physics, and is based on blockage and starvation and work sampling, looking at the buffers and at the actual process states. So this is the good news, but there's a second issue, which is that this procedure works very well in a straight material flow. It gets far more challenging when you have a job shop system excuse me, where there's no straight flow. And today we will learn about this application in the BMW presentation. We have a flexible manufacturing system for automotive engines. And just to give you a feeling, this factory, this part of the factory here, has probably the size of a football pitch, and it's pretty intransparent for the operators. In particular, as there are many breakdowns occurring in the system, and it's very hard to set the right priorities for debugging these breakdowns. And our aim is actually to identify and detect bottlenecks emerging in the system before they actually occur, to set countermeasures. And let me briefly explain what the setup is. So as the system is highly intransparent, we are making use of a virtual twin of this system, and the virtual twin is based on MES, Manufacturing Execution System data, which is, I would say, pretty much real-time data based on the discrete event monitoring in the system. And we are using this data to detect critical patterns within the system. And not surprisingly, we are using rapid miner to design, to derive and apply, in this case, applying a prediction model for bottleneck detection, which ends up in an operator assistance system, for example, based on a smart device. So that's the key idea. And one of the main challenges was that how actually train the prediction model to the required accuracy. And we are actually facing the problem here that we have partly unbalanced label proportions. We have small samples for some labels. And that's why we came up with the approach to actually create the training population, the training data, using discrete event simulation. So this is in fact a second virtual twin of the actual system, which is a plant simulation model, which we use for creating structured data sets as training input for the prediction model. And Mr. Krenner will explain in his talk today more in detail how this actually works. So it's really training with simulation data, and the application of the model is based on real-time, on real MES system data. So the whole, or again, the task of getting the data right is most critical within this use case. And as we've already touched on debugging breakdowns, which is reactive maintenance, I would like to move to another field where actually industrial engineers are strongly involved. And this is all about maintaining production systems. And I have to admit, I'm not a maintenance expert myself, but I did a lot of suffering during my time at Bosch as a plant manager from badly or poorly maintained equipment if you want to keep up your performance. So, and I clearly see the potential of predictive data analytics in the field of maintenance. So just have a look at the current maintenance practices which you find in the field. So of course there is reactive maintenance, and it is good practice when breakdowns occur that you actually look into the root causes. So like in quality management, cause and effect analysis in order to solve the root cause of breakdowns in all or many companies, at least in the automotive industry, this is state of the art. But I mean, only reactive maintenance is not good enough, so you have, of course, the preventive maintenance strategies, which you know from your car, for example, that you get a reminder when the yearly inspection is on schedule. So it's not necessarily that a breakdown might occur. It's just the routine to take preventive action, and moving to inspection-based maintenance. I mean, this is another preventive approach, which takes more the actual condition of the equipment into consideration. I believe Ralf Klinkenberg mentioned the example from concrete drilling this morning, which is based on condition monitoring, and this inspecting equipment in regard to the condition. I mean, this is not necessarily a manual task. And looking at predictive maintenance, I've picked the use case we are working on with BMW. This is not engine production, but the final assembly in the car. And in this short sequence here, you can see the actual use case. It's the monorail conveyor system for car assembly. And fortunately, there are very rare breakdowns of the system. I mean, if this system breaks down, it's fatal, and it doesn't occur very often. But when it happens, it's really a disaster. And what we actually did, again, in order to get the data right, we applied cyber physical systems, which is a sensor kit including sensors, microcontroller, and connectivity, which is based on a banana Pi. It's like Raspberry Pi as a hardware, and the result is quite similar to what you find on the market, like, for example, the Bosch XDK sensor kit. However, this banana Pi application is more powerful, and every carrier has this cyber physical system to gather the data, and from these sources of data from the sensors, the signals, the data is basically forwarded into an IoT cloud. I believe in that case is I'm not exactly sure. It's either the Microsoft cloud or it's SAP HANA, which is used as the data warehouse. And here the data is linked to PLC signals and fault messages from the maintenance system. So the labels coming out of the fault message system, the maintenance system, and I believe, Katharina, you mentioned the issue with timestamps, matching the data, and in this application here, that's a significant issue to get the timestamps and the matching right. And we've been working on this for, I would say, the last 2 years now to get the data right. And now we've reached a point in the project where we can actually think about creating and selecting the right prediction models. And again, we are using RapidMiner for that. I would like to mention one point which is critical, which is the feature extraction, as we have time series data streams here, and the feature extraction is quite a challenging task, which goes so far of applying Laplace or Fourier transformations in order to extract features here. We have another issue in this use case. As I mentioned, fortunately, breakdowns of the system are very rare, meaning they are it's a very robust system, which is good for the business, but not that perfect for machine learning, as we have highly unbalanced label proportions in the training population. And we are still excuse me, working on that point, how to get how to sort out this recall problem. In fact, these unbalanced labor proportions, this is a key challenge which we probably find in most use cases where we are dealing with quality management and quality assurance. And this is my last use case for today, my presentation. I mean, we've already learned from Katharina how huge the potential of data science is in regard to quality management, which is yield management, efficient quality gates. And if you look at the state-of-the-art methods and tools in that domain, I mean, FMEA, product process FMEA, that's how you start with setting up the quality management for your processes. You have massive inline and end-of-line testing. So, for example, today we have a lot of participants from Siemens Amberg, which is a very famous Industry 4.0, very advanced plant. And in order to assure the high quality of products, they do massive testing have massive testing equipment in their value streams. And we find it all over automotive industry. And you can easily imagine that this is very costly and takes up many resources and actually production time. But this is state of the art. As well, statistical process control is state of the art. However, we found in some projects that due to long testing time, you cannot do 100% testing, but sampling only, which creates some issues. And last but not least, talking about state of the art, there's, of course, Six Sigma methodologies, and I believe many of you are familiar with DMIC. And the interesting thing is that the DMIC circle is not that far off the actual CRISP process, where you have to undergo iterations. And I believe I can save some time on this example, as Katharina talked in more detail about it, which is the steel rolling mill use case, and this afternoon Mr. Lieber will present it in detail. The idea is you want to have very tight quality loops within your value stream. And when I'm talking about quality loops, I do not necessarily mean feedback loops, but as well, when we are talking about prescriptive analytics, we're talking as well about feed-forward loops. And I've seen one approach in the wafer manufacturing at Bosch in Reutling, where they are working on feed-forward loops. And of course, you need data analytics for that. So in this slide here, you get an idea that we have very tight, very short quality loops within the value stream. There's no need to explain the feature extraction again. What might be interesting for you is in regard to the prediction model. We really like when we have a new use case to start with unsupervised learning for anomaly detection, outlier detection. Moreover, if we have missing labels, label issues, we had one project where we actually created labels based on unsupervised learning on anomaly detection, which worked pretty well if you compare machine learning with the domain knowledge of the experts. And as I mentioned before, the unbalanced label proportions, that's really an issue, because if you want to substitute a real quality gate in a final test project, you do not want to predict a true positive as a negative, because that would mean bad quality slipping through to your customer, which can be a disaster. And on the other hand, you do not want to have pseudo faults as well. So this confusion matrix here, this is something, well, in most projects we look into this in very detail, and it's not the and the prediction accuracy, as you can imagine, is not the only critical KPI when it comes to quality management. As I said, prescriptive analytics, the idea is to implement the prediction model into the process, which is linking it to the process PLC, or SPS in German, and there one issue is, as Katharina mentioned, when the environment or the product range is changing, your model is losing accuracy and you have to pick another model. And this is this challenge is something we want to address, hopefully in the next phase of the collaborative research center. So maybe just to summarize, key issues in regard to industrial application, in many cases, is data cleansing, data pre-processing, the issue of the label proportions, and model management. From our experience, these are very common and usual challenges in applying data science in industrial use cases. And coming to the conclusion of my talk, the key question would be how could you overcome these challenges? And one key factor to successful projects is really combining expertise in machine learning with domain knowledge. And I mean, that might sound like a motherhood statement to you guys, but I know many companies who have started to employ data scientists, and there are really massive communication problems between the data scientists and the domain experts, as a lot of information is lost in translation. They do not talk the same language. And I personally believe it would be very helpful to actually build up expertise in regard to machine learning and to qualify the domain experts into this direction towards data science. I mean, we've learned from Katharina that actually applying RapidMiner is not that difficult, but at least you got to know what you are actually doing. And I would say a bit of knowledge in regard to statistics is most helpful in that case. So with this, I know some companies who are pursuing this strategy and building up data science expertise within the domains. And I personally believe that the Department of Industrial Engineering, of Quality Management, there could be pretty good foundation as organizational entities within a factory to build up this knowledge, as they have a tradition in providing facts and figures based on data. And this is at least a strategy which I'm pursuing here in Dortmund with my department for several years now, and it's actually working out pretty well. So I would like to encourage you to try this experiment and build up industrial data science knowledge within these organizations. So I hope you will enjoy today's presentation and the conference. And I'm fully aware that the invitation for this year's conference was a bit short notice. So next time we do it a bit earlier, and that might give us a chance to even pick more attractive location than the university campus, which is an old coal mine. So that might be an appropriate place to discuss data mining. Thank you for your kind attention.
Questions? So you said that, as Karina also said, that timestamps and getting patterns right is a very big capital in industrial data science. How do you tackle these problems? You can't throw away the data, you have to correct them, right?
Well, it pretty much resembles, I would say, criminal investigations. Yeah, that you really try to set jigsaw pieces together, and one approach was we look at the value stream and we look at the sources of data which in the value stream, which are very various and inhomogeneous, and we really try to match it, to link it, and of course link it in regard to time and timestamp. And this is, I would say, this is really bean counting work. It's a lot of effort, and usually you have to approach many experts from your industrial customer for that, because you need IT experts, you need process experts. So it's really a kind of investigative job in the first place. And once you've made the link, most likely you would have to make adjustments to your IT system. We've experienced this at BMW, at Deutsche Edelstahlwerke as well. I'm sure you did it in your projects as well. So it's the nature of the beast, I would say. So it's really, you have to be brave and busy and endurant. Another Masoret statement, sorry about that.
My question might go into the same direction. If you use more sensors, more sophisticated sensors, what does this mean for your data preparation task and for the modeling task? So I've heard that in many industries, companies include more sensors to their production.
Okay. What, in your definition, what is a sophisticated sensor?
What precisely? Keep the term sophisticated and say you add more sensors. So automotive industry is quite advanced, and I see that many industries are not that far away. They have a long time frame for using their machines, and they adapt to new sensors.
Mm-hmm.
So does it mean more complex preparation tasks, so constantly working on your models?
Mm-hmm. It's quite a difficult question and very difficult to answer in a short time. So I would say in regards to what is a good sensor, I would say firstly it should be robust, because you don't want to have missing values. And of course you want to have consistent values. So you want sensors which work very reliable. It's probably even more, from my perspective, even more important than the precision. Of course, the accuracy has to be sufficient for the use case. And I mean, we are running into an issue. You mentioned that more and more sensors are applied to increase the data volume. It's not big data yet in comparison to the astrophysics use case we've learned this morning about. But it's increasing, and it puts the transmission rate in wireless transmission in factories to a limit. In particular, when you want to, if you're transmitting complete data streams. So the challenge might be, and then probably we are really talking about sophisticated sensors, when you have sensor kits or embedded systems which allow you to do some pre-processing of the data right at the data source. That once you know what the right aggregation and the right features are to extract, you do not do it centralized, but you do it at the source to reduce and to limit the amount of data you got to transmit. Because one challenge in production, if you're talking about advanced process control, it's of course the time resource. And ideally, you want to do it in real time, or at least quick enough for your PLC to cope with the input. Would that be okay?
No, that's fine.
Yeah? Okay, thank you.
You talked about the challenge of training machines to recognise breakdowns when breakdowns are very rare. and you talked about anomaly detection as one way of tackling it. Do you think you can get the precision and your predictions that you need from anomaly detection? And if not, what else are you trying?
Wow, that's a question which probably requires an expert. Looking at Katharina, I mean, this goes deep into machine learning. So you're talking. So it's, you would say it's. I mean, there are two issues. There's the label proportions, where I would say that with an active learning approach or generating a training population and a sufficient set of labels or samples for a specific label based on simulation, I would say this could be overcome. Could you just once again ask your question, please?
Maybe I jump in.
Please.
So there are two issues. On the one hand, you're right. With anomaly detection, it very much depends on the data, whether we get a very good rate or not. So, and that is also why I had in the example so many models, so that we have a certainty measure on top of it, so that we only inform about the successful. So that's the one thing. That is dependent on the data, and therefore, in general, I cannot say whether. We'll get a good result or not, because it depends on the data. With good data, we get a good result. With bad data, we don't. So that's the one thing. But I think that very important part of the search for anomalies is the start of the interdisciplinary dialogue. So by using this as the first step, and that's why I focus so much on producing the information such that we can talk with the expert. And then by this talking with the expert, we get at new, better insights and can then design the further learning steps. So actually, I would always say anomaly detection is a very hard learning task, because it has a learning task in it, estimating what's normal, and then putting something on top of it. So it is a very complex task from the learning perspective, but it is a first step for interdisciplinary talking, and at the end of that, we'll get at something more useful than anomaly detection.
And it doesn't hurt actually to start with unsupervised learning when you tackle anomaly detection. I mean, we had one case where we get exactly this dialogue with the domain experts based on an unsupervised approach at the start.